right, so where were we? So the class met Monday, Wednesday, Friday, and the section met on Tuesdays and Thursdays. So they went to the section on Tuesday and Thursday. That's when the second midterm would be turned back to the students. And then those that they didn't reach in section, they then went to the class on Friday. And so 91 of the 95 students chosen were actually reached and willing to complete the survey. So I want to show you before we do any analysis and before we actually let's flip over and let's fill out another one of these diagrams for this group of people. I'll have to make one up. I only have one. All right, so here's our target population and our sampling frame. All right, so what's our target population? Students in Stat 2 in 1994, right? So I think it was fall 94 Stat 2 students. What's our sampling frame? How do we reach them? The list of students who took the second midterm. Do we have any ineligible units in our sampling frame? Is there anybody that we might have accidentally sampled? What do you think? Can you think of one? I'm having trouble coming up with, what's that? Who took the test? Okay, good. All right. Good one. An auditor? Or concurrent enrollment? Who took the test, right? So they're officially not the students in the roster, in the official roster. How about, I'll extend this. What about the ones that we don't reach that are, or the ones, in the sampling frame that are non-response? Who are those? People who didn't show up for section or for class on Friday, right? So these are the no-shows on the Tuesday, Thursday, and Friday after the exam. What's this group here? Not only the no-shows, it's also the ones who refused to participate, right? You didn't have to participate, so the refuse to participate are also in that group. What about the that group right there in the center that's circled? So that's a sampled population. This is the sampled population. So it's not just the 91 people that we got the surveys from, but it's anyone who we could have gotten a survey from. So those are folks what we got the survey from them. They took the exam. They came to section or class that week, and they agreed to participate. And they are officially enrolled in the class. Now, what about this piece out here? Target population that we don't reach through the sampling frame. Yeah? Yeah, someone who did not officially enrolled, but didn't take the second midterm. And there probably aren't too many of those. This was before the 5-week drop deadline, so it was possible that there were people who were still enrolled but hadn't taken the exam. So that's how we would divide up the target population from the sampling frame, from the sample population, talk about the non-response and the ineligible. All right. Just briefly, I want to show you some of the questions. You'll be working with these data on your next homework assignment. So one of the questions was, how much time did you spend last week playing video and or computer games? Come on, be honest, this is confidential. You could say no time at all or fill in the blank, that many hours. Then the second question was, do you like to play video computer games? You had to circle one of these. You like very much, you like somewhat, didn't really like it, you don't like it at all, and you've never played. Anyone who circled not at all or never played was told to skip ahead and go to question 9, and that was demographic information about what year you are, what your major is, what gender you are, that kind of thing. Then the questions 3 through 8 were about video game usage, and question 6 in particular was, how often do you play? Circle 1, daily, weekly, monthly, semesterly. Why do you think, let me ask you this, why do you think they would ask these two questions, question 1 and also question 6? And what do you think about the order of those questions? So. It's the other way around. If you ask them a general question first, then the specific. I'm looking at, you're right. Then the specific tends to be more accurate, I believe. But now you've got me questioning it. And why would you ask these two questions? So yes, that's one notion. Why would you go and ask these two, get these two pieces of information? Yes, in the back. Right, maybe last week you were very busy and didn't get to play your usual amount of time. Why might that be the case? Because you had a midterm that week, that's right. Were you going to say something different? Same thing? How about one more reason? Does anybody have another reason why you'd ask these two? That's right. So you might, if they play monthly, they might not have played that last week. And so you'd want to get a way to measure how much they play using two different questions. And so this second question, do you play daily, weekly, monthly, semesterly? You would be able to see whether or not people, even though they didn't play last week, they do play regularly. And the monthly folks, you could easily not have been able to capture. Another is that you could sort of check on the internal consistency of the answers to those two questions. So if people play weekly, how many of them do you think, if people only play monthly, how many of the people who said they played monthly would you have expected to play the prior week, roughly? Yeah? Right, 20-25%, exactly, because how many weeks are there in a month, and what's maybe actually less than that because of the midterm, but you would want to see roughly about a quarter of them have played the prior week. So we just filled this one out, and we can now go through all of the pieces. The observational unit are the Stat 2 students. The target population are all students enrolled in Stat 2 in fall '94 at Berkeley. There's 314 of them. The sampling frame is a list of students who took the second midterm. The sampled population are students who attended section Tuesday, Thursday, or class on Friday, and the week after the second midterm and agreed to participate. And they also took the exam, right? And the sampled unit is a student on that list of those who took the exam. Okay. So before I tell you all the answers, let me ask you this. So the students took a simple random sample. The 131 students took a simple random sample of all the people that had the list of people who had taken the midterm, the second midterm. What does the simple random sampling do for you? Use what you know about randomization from design of experiments to try and think about what a sampling process like a simple random sample, which is you put all the names in a box, you shake all the names up so they're all clipped out, one ticket per name. You reach in and you pull them out one at a time without replacement until you have 95. So that's the process of a simple random sample. It's drawing tickets from a box without replacement. So you've been working with that a lot with hypothesis testing and also with your central limit theorem homework. So I've got a couple of questions for you. Or why do you think this process of simple random sampling is a good one if you want to make some kind of comment about the population? Why was it good for design of experiments? And why is it good for, in terms of what your current homework is about? Those are two ways that you can bring, or two ideas that you can bring to answering this question. Why a simple random sample? Yeah? So chance is really is crucial here, right? You can actually calculate the chance that any particular person winds up in the sample. That's right. And in fact, with a simple random sample, they're all equally likely from your sampled population piece. That's right. And why is that good? Yes? So you can, and I'll stretch it a little bit further. Why can you go from the sampled, your sample to the population? It's related to this. It's related to this chance notion. What do you think? I mean, you're right. Yeah, why is that? Why do you think that will work?
Because you're getting really close to, like what we're doing in our own decision, getting really close to what would be normally the chance of.
So you've got two ideas there that are both good ideas, and they're both what I'm looking for, but I want to try and separate them out a little bit. First, what were you gonna? You wanted to volunteer something?
I was just going to say that your sample population is going to approach like a bell-curve style distribution.
That's what you were talking about. I'm going to hold that for a second and say the other thing is that your sample, because of this chance process, your sample is going to look roughly like the population. So that's an idea that's similar to what in design of experiments we used randomization to sort of even everything out. Here we're using randomization to say everybody's got a particular chance to be in my sample, and with a simple random sample it's all an equal chance, the same chance. So I can then conclude that my sample is likely to look a lot like my population. I need that to happen for my estimates for me to draw an inference from my sample to my population. So that's one distinct piece. The other is what you are also getting at is the central limit theorem tells you something about if I take an average or a sum or some kind of statistic based on my sample, I can use that as an estimate for my population, and I know something about its probability distribution. I know that it's roughly normally distributed for a large enough sample size. And I know that because of the box model that's underlaying it, and because I have a large enough number of draws. So that's two really important things. The random selection process gives us samples that tend to be representative of the population, as opposed to some other kind of process where, like haphazard sampling or quota sampling. The random selection process means we can use chance to determine the chance that someone is included in the sample, and we can figure out the probability distribution for a statistic like the sample average. And that's what you were getting at. So in particular, here's some more terminology. There's what we have is called the population parameter. That's the summary statistic of the population, and we don't know it. So in the rural drinking wells, we don't know the average level of pollution or pesticides in these rural drinking wells. Or we don't know the proportion of rural drinking wells that are contaminated. Those are two different kinds of statistics, and we don't know the answer to them. So those are population parameters. Population meaning they're about the whole population. Parameter meaning it's sort of a piece of information. And these are unknown. So the parameter is not known, so we take a sample. Because we're taking probability or chance, using a chance process to take a sample, we can then start computing probability distributions for our sample statistics. So we use a summary statistic of our sample, and with the wells it would be, for example, the proportion of wells in our sample that are contaminated. And that proportion we think is a good estimate for the proportion in the population. Why? Because we've been able to use chance to take a representative sample. Not only that, the central limit theorem tells us something about that distribution. It tells us that the sample average should have roughly a normal distribution. And we can even compute its spread. Okay, so that's what we're going to do. We're not going there yet. I'm going to switch over and do a really simple example with the document camera. All right, so this gets back to really, really simple things. That's my population there. It's a bag of chips. And we get to peek in it a little bit. The chips are worth different dollar amounts. The white chips are worth $10. The blue chips are worth $20, and the red chips are worth $60. And just by looking at it, you can kind of tell that maybe it's not a uniform distribution. I'm interested in what's the average value of chips in my population. So that's my question. What's the average value of chips in my population? So here I am in the lucky position of this is both my target population and my sampling frame. My sampled unit is the same as my observation unit. I don't have to worry about non-response. I can pull out one of my units and say it's white. It's white. Therefore, it's worth $10. I don't have to worry about non-response, any of that stuff. Okay? So what I'm trying to estimate is what I would like to know is what's the average chip value. And so this is our box model. I have a bag instead of a box. I have chips instead of tickets. But it's the same idea, and I can draw without replacement from here. And I start making draws. I got a white one. You can see what I'm doing. I'm not looking. Another white one. A red one. A blue one. And I keep going, right? So I can, this is a sample of 4. I've got 2 whites, 10 each, a blue for 20, and a red for 60. So I could take an average of that and use that to estimate the average for my population that I'm not observing. So that would be 10 plus 10 is 20, plus 20 is 40, plus 60 is 100, divided by 4 is 25. So that's my sample, and I can take a sample average, which is 10 plus 10 plus 20 plus 60 over 4, or 25. Over here, what I want to know is the actual population average. That's my unknown. So what do you think? Is 25 a good estimate for the unknown population? Why not? You think my sample is too small? Yeah? Yeah, that's a really good idea. Unfortunately, in this case, we could do it because they're just chips and I can do whatever I want with those chips. In the real world, when we've got drinking wells or children, we can't just keep and a budget, we can't just keep taking samples. And so what you're doing in your homework by repeating this process over and over again is a way to find that probability distribution. We can't do that here. We have to sort of know what we get one shot at it. We get one sample. You're complaining that my sample's not big enough. That's a legitimate complaint. It actually is, what's the expected value for a sample of size 4 from this bag? Yes? Well, it does depend on the population. Not so much, you're talking about accuracy, but I'm asking a different thing. What do I expect to get? If I draw 4 tickets from the box, take the average, what do I expect? Yeah, so we have to do this in a very abstract way. That's right. We don't know what's in that box. Well, we could look, but I do know that okay, let me back up. What's the connection? What is the population average? How do I compute that? In terminology you know already with boxes? Yes? The ticket values times their proportion. Or, that's right, and another way to do it is simply take the box average, right? The population is all the chips in that bag. So the population average is just the box average. I don't know what it is, but I do know it's the box average. So I'm going to go back to my first question. I take a sample of 4, and I take the average. What do I expect to get? What's the expected average? That's the one I actually got of 25, but what do I expect to get? Yes? Exactly. It's the box average. Why do I know that? That's right. Is the expected sample average, is the box average. That doesn't mean that I got the box average with my particular sample of 25, but it means that's what I expect to get. That's why we do this kind of sampling. This simple random sample tells us that what we expect to get for our sample average, no matter how big or small our sample is the box average. Now we'll go back to your complaint that that's only a sample of 4. So you don't think it's that good of an estimate. Why not? You're right. It's not that good of an estimate, but it is the case that what I expect to get is the box average. Yes? The law of large numbers tells us That's right. The law of large numbers tells us something about the spread. What's the deviation? What are the typical deviations of our sample average from the expected? And that's related to the square root of the sample size. So it's the SD of the box over the square root of the sample size times something you've been studying for this homework, the finite population correction factor. So you know if you only have 4 samples that you're going to have a really big spread. And so you want to take more samples. You want to take a larger sample size so that your sample average is closer to the expected sample average. All right, so I want to show you this model that I have that I think is really helpful for thinking about this world. It can be a little confusing. And so I think it'd be really helpful if you take a piece of paper, turn it on its side, and divide it up into 3 columns. And label it across the top. Population on the left, my sample on the middle, sample average, and if you want to say probability distribution or something related to across the right-hand column. Of the sample average, right? Okay, so what the left column, is the population. That's the thing that we don't really see. That's what's in this box here. That's over here. That's my population. I can actually look in that box now because it's a simple little box, and I can draw I can draw the distribution of values in the box. And we know, I've already told you that there are only 3 values, 10, 20, and 60. And in fact, there are 200 chips. In fact, I couldn't quite fit them in. There's supposed to be 200 chips in this box. There are 100 of a value 10. There are 80 with a value of 20, and there are 20 with a value of 60. So this is the dollar value, and those are the counts for my population, what's in this bag, okay? So I can describe that distribution by making a distribution table of the different values and the proportion in my population. Their values are 10, 20, and 60, and the proportions are 0.5, 0.4, and 0.1. So that's in my population. 50% are $10 chips, 40% are $20 chips, and 20% are $60 chips. I can find so my population size is the next thing. It's 200. My population average is my box average. There are a couple ways to do that. Tyler says take each of the values and multiply them by the proportion. So that would be 100 times 0.5 plus 10 times 0.5, thank you. 10 times 0.5 plus 20 times 0.4 plus 60 times 0.1. Or I could just add up the value on all the tickets on the box. So I'd have 100 10s, I'd have 80 20s, and 20 60s, and divide by 200. And either way, I find it's 19. That's the box average. The box SD is the population SD. Remember how I compute that is I look at all the different values in the box, and I have my 10s, and I subtract 19. I square it. How many do I have like that? I've got 0.5 plus ... Or I just take the SD of the whole list. Either way, and I get 14.4. So the average value is 19. The SD is 14. That says that if we tried to find the balance point of that little diagram that I showed, it would be roughly at 19. And that the typical spread of where I might find actual chips from the 19 is about 14. Okay? All right, but then there's my sample. So earlier today, I took my own sample, and this time, and I agreed 4 was kind of small. So instead, I took a sample of 25 chips from that bag. And I found that, I'll write it down here, I found that I got chips marked 10, 20, and 60, and I got 44% or 11 chips marked 10, 44% marked 20, and 12% marked 60. I could make a sample distribution, 10, 20, 60, and so now with my sample, I've got an equal number of 10s and 20s, and I've got fewer 60s. So notice that my sample, it's not exactly like the population. This looks like the population, but it's not exactly like the population. I wound up getting the exact same number of white chips and blue chips, when in fact we know there are more white chips than blue chips in the actual population or the box. I can compute it, so my sample size is 25. I can compute a sample average, which in this case was 20.4, and a sample SD, which in this case was 15.3. So they're not exact again, but they are similar to. So the question is, I don't see this. Why do I bother taking a sample? I don't take a sample if I know what's in the population. I just go with the population information. I only take samples when I can't look at everything in the population. So then I take a sample. And so this is my sample down the middle. And I want to say, I'm interested in knowing the average chip value in my population. And that's 20. And then you say, well, what more can you tell me about how accurate your estimate is? That's when we come over here to what you're doing on your homework right now, is you're figuring out the probability distribution for the sample average. And that gets at what you were trying to say, which is, well, if I could do this over and over and over again, I would have an understanding of what kind of typical deviations might a sample average have from the box average, and what does that distribution look like? And so I did that in R, and I used the replicate function, and I took 100,000 samples of 25 draws without replacement, each time taking the average. And I got something that looked amazingly normal. And its center was what? Was the center 19? Was the center 20? What was the center? 19. It's centered at what we expect. We expect the box average. Its spread, which is how far away might an individual sample average be? What's the spread? Is the spread 14? Is the spread 15? Is the spread 14 divided by the square root of 25 times the finite population correction factor? I think so, right? Which is roughly 2.7. So the spread is the box SD divided by the square root of the sample size times the finite population correction factor, which is 200 minus 25 over 200 minus 1, which is about 2.7. So that says that there's one unfortunate thing, is we don't know the box SD. So what do we do if we don't know the box SD? Use the sample SD. So if I plug in the sample SD, which is 15 instead of the 14, I'll have my estimate's going to be close. It'll be 2.8. I think, if I've done that correctly. So I can say that I took a sample. I got 20.4 as the average chip value for my sample. And I can say, how accurate do I think that is? I would say it's roughly plus or minus 2.7, we'll continue this on Friday with confidence intervals.